Welcome to this fourth part in this video tutorial series about the OpenGL API. So in the previous part we worked with some basic animation and we had this output. So in this part we're first going to work with colors and then we'll have a basic look at translation. So I have already explained to you how the RGB values work, how you can use the RGB values to set a background color for the window. So we'll use the same technique to set the color in which the primitives are drawn. So in OpenGL actually the color is a state variable. Now I'll explain to you what that means. OpenGL is a state machine and it stores its various states in state variables. So one of those state variables is color. So by default the color is white. If I build and run this application, you can see the default color of the primitive is white. We did not explicitly set any color to draw the primitives in, and this is being drawn in white color by default. So that means the white color is the value of the state variable when the OpenGL starts up. So white color is the current value of this color state variable in OpenGL. So now if you change it to a different color, like I change the state variable to blue, now all the primitives after this will be drawn in blue color unless I change it. So let's say that I change the color to blue, then I draw a square. The square will be drawn in blue color. And then I change the color to red. And after that I draw another primitive which is a circle. And that circle will be drawn in red color. So when this primitive was drawn, the value of the state variable was blue, so this primitive was drawn in blue color, and after that the value of the state variable was changed to red, and after that all the primitives that will be drawn in red color unless the color variable is changed again. That is how it works. So now I'll introduce you to the function which is used to change this color variable. So the function is GL color. I'll just give an introduction of this function. Inside the NIT function, we'll call this from inside this function. So the color function has various forms you can see here. So it has two postfixes. The first one specifies the number of arguments. So if you have 3, that means 3 arguments, which are red, green and blue components of the colors, and 4 means the red, green, blue and alpha components of the colors. We're just going to work with RGB. And one more thing I need to explain to you is that the mode, if you want to use the alpha value, you need to change the mode. So inside the GLUT NIT display mode, we initialize the display mode to GLUT RGB. So that means the red, green and blue components will be used. If you specify to RGBA, that means you'll also use the alpha component. But since we're just using the RGB components, we'll not specify alpha. So GLUT RGB, and we'll just use the 3 arguments up here. And the next postfix to this function is the data type of the arguments. If I set it to F, that means the float arguments of the type float, or D means double. So it is always convenient to use float or double to specify the intensities. If you use integer, now since you cannot have decimal value, so the minimum value for an integer will be 0 and the maximum intensity of the color will be 255. But in case of floats, like I already explained to you, the minimum intensity is 0 and the maximum is 1.0. This is because you can specify the floating point values between 0 and 1, like 0.5. So it is always convenient to use floats or doubles. So we'll use this form of the function in this tutorial. So this works just as the same way that the clear color function worked. We worked with this in the first part and we set different colors. So I'll set the intensity of red to 1, green to 0 and blue to 0. Now the state variable is of red color. So that means the primitives that I draw will be drawn in red color. Now let's build and run this application. Now you can see that the primitive is being drawn in red color. So now this actually is not a very good place to call the function, because you might want different primitives in different colors. So I'll remove it from here and I'll paste it at the place where we are drawing the primitive. So I begin drawing a polygon, then I set the color of the polygon and then I draw the polygon. Now after this all the primitives will be drawn in this color. So if I want to draw a polygon in different color, what I'll do is I'll change the color to something, and then I'll draw my next polygon if I want it in different colors. Now I can draw two polygons after this, and they'll be drawn in this color. And one common misconception that people usually have here is that a color is assigned to a full primitive. A color is not actually assigned to a primitive. A color is assigned to each vertex. The color is red means all the vertices that follow this color definition will be drawn in red color. So all of these vertices are drawn in red color. Now if I change the color before I finish drawing the primitive, so like I change it to green, so now the first two vertices have red color and the next two vertices of this same primitive have a green color. So if you want to see what happens in this case, you can build and run the application and see for yourself. Now you can see that the left two vertices have red color and the right two vertices have a green color, and the color is equally blended between these two vertices. So that is how it works when the different vertices of the same polygon have different colors. You can also try specifying different colors to all of these vertices. The second vertex will have a mixture of red and green, and the last vertex will have a blue color. Now I'll build and run this application and check what it looks like. So all the four vertices now have different colors. And the next thing I want to tell you about that this type of shading which enables the blending of color is called smooth shading. You can actually change this shading. This is also actually a state variable GL, which is GL shade model. So this function will be used to change the type of shading. So currently it is GL smooth. This is the default shading type, which means that the blending will occur. If you set it to GL flat before drawing the primitive, the blending will not occur. That means the color of the first vertex of the primitive will become the color of the whole primitive. So in this case the color of the first vertex is red, so that means the primitive should be drawn in the red color. So this is what happens when you set the shading to flat. Just like you can set the different colors, just like you can set different colors for different primitives, you can also set different shading for different primitives. Like I change the shading to flat here, and then I draw this primitive. After that, I can change the shading to smooth here, and then the primitives following this will be drawn in the smooth shading. So it is usually better to keep the shading smooth. So this is about colors. So one final point I want to make is that you can have your GL color. So you can have these calls to change the color state variable in between the GL begin and GL end calls, and it'll work fine. So like I call this function in between these two calls, and it works fine. But this is not the case for every other function in OpenGL. Just like the matrix transformation functions, rotation, scaling, translation do not work between these two functions, GL begin and GL end. So you have to call those functions from outside these calls. But the color 3f works fine, and you should keep that in mind. So that was about colors, and now we'll move on to translation. So translation is actually a type of matrix transformation. So matrix transformations are of three types: translation, rotation, and scaling. We're just going to work with translation in this part. We'll work with translation in 2 dimensions. So translation is actually shifting of the origin. So let's suppose this was your coordinate system, and these are the divisions. And now the point 1, 1 lies here, and if you draw an object at this point, it'll be drawn here. Let's suppose this is your window. So but before you've drawn the point, before you've drawn the object, you translate to a point which is 3, 3. So 3, 3 lies here. So translating to 3,3 means moving the origin to this point. So if you move the origin to this point, that means the coordinate axis will shift here, and these will be the new divisions. And now the point 1,1 will lie here in your window. You can see inside this window the point was earlier here and now it is here. So just using the translation you can change the place at which a primitive is drawn. So that is the most basic application of this thing. Now you need to make a mental note that you need to translate before you draw. Like for example, I draw a square here and then I translate my origin to this point. Now this translation will not alter the geometry of the primitives that have already been drawn, like this square. The place of this the place at which this square is drawn will not be changed. So to avoid this, you first need to translate and then you need to draw the object. So that is exactly what we're going to do here. We were using this exposition variable to change the position of this square, but to keep things simple and avoid confusion, we'll just make it a regular square which is drawn along the origin. So I'll change its geometry. And now you can see that this geometry is of a square which is drawn around the origin. Oops, there it goes. So this is actually now a geometry of the square that is just being drawn around the origin and is not undergoing animation or anything. So to avoid confusion, I'll just comment all of this code that we were using to animate it. So this is just a regular square. Now we'll use the translation to change its position. Now if I translate the origin to 5,5, so in this application our origin lies at this point, and now if we translate it to this point, which will be 5,5, then the square will be drawn at this point here. So you can actually try that. And now before I draw, you need to remember, before you draw you need to translate before that. So the function used to translate function which you use to translate the axes is called GL translate, and there are two forms, translate F and translate D, which specify the type of the argument. So we'll use the float type, and it takes the arguments, which is the point to which we want to translate. So the x, y and z coordinates of the point to which we want to translate. But since we're working in 2D, you can just avoid using the the third argument, which is the distance on the z-axis. So I'll set it to point 5.0, 5.0, and the z coordinate will be 0. So now I'll build and run the application and see if the square is being drawn at the right position. So there it goes. The origin was before we translated the origin was at this point, but after translation the origin was shifted to this point, and the geometry of the square was drawn around this point. So using translation you can change the place at which a primitive is drawn. This is more useful when you have your 3D models saved in your files. So you can just load the model which has its geometry around the origin. And now if you want to draw it at multiple positions, you can translate to a point, then you can draw it, then you can translate to a different point, then you can draw it again. So that'll help you draw the same primitive at different positions without altering its geometry. So this same geometry can be used to draw the square at different positions in your program. And now we'll have a look at how translation can be used for animation. So before that we were using before that, I need to make a point that this load identity function is actually used to reset all the matrix transformations. Inside the model view matrix, it resets all the transformations or all the changes that have been made to the coordinate axis. So that's why, because you can see that every time the display function is called, the GL translate f function is called again. But this load identity function beforehand resets the coordinate system. So that is how it works. For the first frame, we reset the coordinate system, we translate to this point, and we draw this square at this point. Then for the next frame, the coordinate system is again reset, so we need to translate again to that point and draw it again. So for every frame, the square is drawn at the same position, because we are resetting the coordinate system. It's not like we in every frame we are translating 5 points above, because if I remove the load identity function, for the first frame it'll translate to this point, and for the next frame it'll translate to a point which is which is at this position relative to the current coordinate system. That means I'll just use the diagrams to explain it here. So in the first frame we translate to this point, and now this becomes the coordinate system, and now in the next frame it will translate to this position, and in the next frame it will keep on translating, and the object will be drawn out of the window. So this is not the case, because every time you call load identity, the origin is reset to its default and it comes here for every frame. So that is the use of the load identity function, because you can start over in every frame. So now we'll talk about animation. So before this part, we were changing actually a variable called exposition, and we were drawing the cube at different coordinates. But now we'll shift the origin to -9. We'll not shift it to -10, because if you draw the square at -10, only half of it will be displayed inside. So we'll shift it to -9, and for each frame we'll keep on shifting it a bit towards the right, and similarly when it reaches the point +9, when the origin reaches here, then we'll keep on shifting it backwards to -9, just like we did in the previous part. But the difference is that this time we'll not change the geometry of the square, we'll just shift the origin. So the default exposition will be 0 at the origin, and we'll use the state variable, this variable, just as we did in the previous part. So now in the timer function, I'll just uncomment this code, and the minimum exposition will be -9, and the maximum exposition will be -9, and the minimum will be -9. I just did it the other way around here. So this is how this is going to work. It'll go from -9 all the way up to +9. This is the point that we want to translate to on the x-axis in every frame. So I'll just remove the translation for y, and we'll translate to x position in every frame. And now I'll demonstrate how this is working. So this is the coordinate system, and this is the square that is being drawn around the origin. So for the first frame you are at this point, and for the next frame it translates to a point here, and this is the new origin, and for the next frame the square is drawn here, and for the next frame it translates to this point, and these are the coordinate axes, and then in the next frame the square is drawn here. Similarly, the origin goes all the way up to +9, and when it is at +9 it starts after that it starts going backward all the way up to -9. So this produces the animating effect of the cube going back and forth on your screen. So let's just build and run this and check if this is working. So this is the same output that we had in the previous part, but this time we used translation and made it look much more simpler than that. So translation is usually helpful in animating when you have multiple objects that you have to animate. You do not have to worry about the geometry of each object. You just translate every object to its particular location. So another note you need to make here is that you cannot call the translate function inside the GL begin and GL end calls. This will not work. If I call this between these GL begin and GL end calls, this will not take any effect. So I'll show you, I'll build it on the application, and you can see that this is not working. So you can see the square is not being translated. So you have to always take care of this, that you should not call this function from inside these two calls. And now I can also translate to a point on the y-axis and see if this is working. The translation on y-axis is constant, it is not changing, so any animation will not occur on the y-axis. The animation will only work on the x-axis because the variable x position is changing for every frame. So the position on the y-axis is constant for every frame, only the position on the x-axis is changing. You can also change the y position, you can animate it like this diagonally if you want. If you want, I'll just do that for you here. I'll change the translation of y-axis also to the x position, and so the translation will occur along a line which is x equal to y. So this is diagonally. So in this case, x coordinate is always equal to the y coordinate of the cube, of the square, sorry. So you can plot a line which represents x equal to y, which will have this plot, x equal to y. So your cube is animated along this line where the x coordinate is always equal to the y coordinate. So that was all about translation, and I hope you have enjoyed the video. So stay tuned and thanks for watching.